Let me start the recording. Okay, so hello everyone. Thank you for coming. Today we have the last seminar of the year because then we're going to take a break for New Year's and for Christmas. And we have Yaqi Duan presenting. And Yaqi is an assistant professor at NYU. Research interests lie in operation research, reinforcement learning, and essentially lies mainly at the intersection of statistics, machine learning, and she's interested in developing theories to address challenges in data-driven decision-making problems. She received the IMS Lawrence Brown PhD Student Award in 2023. She got her PhD from Princeton University. I think before that she was studying in Peking. And prior to joining NYU, she was a postdoctoral researcher at MIT with Martin Wainwright. And I believe that is where she did the work she's going to present today. So, Yaqi, thank you very much for joining, and you can start presenting.
Okay, sure. Yeah, thank you so much for the kind introduction, and I'm very happy to be here to present our recent work. So like this, online webinar has been like very special, meaningful to me because like during the COVID, it's kind of like form a community for us to discuss all those RL theory ideas and to connect with people all around the world, and like I have like previously my two of my advisors presented our work in this webinar, but like it's very happy for me to get this chance. So like this time I'm being the presenter for our newly developed work here. Okay, so in this work, I'm going to introduce a new framework for the RL theory analysis, tackling the continuous state and action spaces. And we are like interested in this new scenario because we have witnessed some fast rate phenomenon in many continuous control problems, but we found that there still exists a certain gap between the current state of the art RL theory and all those continuous control phenomenon, and we want to develop a new framework to characterize the theoretical foundation for that fast rate phenomenon, and that is like our main focus in this work. And this is a joint work with my postdoc advisor, Martin Wainwright. Okay. Oh, so here's a brief recap of the RL problem. So our goal is to learn an optimal decision policy pi based on our observations of the interactions with a dynamic system. And the policy we learn is denoted by pi hat here. And in this RL framework, we assess the quality of this pi hat using this value gap notion. So it basically compares the expected value of the pi hat when executed in the true dynamic system compared with the best possible value that can ever be achieved by any policy. And this difference is the assessment for us to quantify how good the estimation of the pi hat is. Okay. And here we are interested in the continuous state and action spaces because it appears in many real-world applications. For example, in inventory control, the replenishment order can vary continuously, and also like in healthcare, the medicine dosage can be treated as a continuous variable. And so okay. So here is a brief recap of what we've obtained from the state-of-the-art RL theory for the quantification of this value gap that have appeared as the major measurement of the quality of this pi hat. So people have tackled this question in different scenarios. For example, in the generative model, or there is a simulator for the dynamic system. there is an offline data sets, and we can only interact, there is no interaction with the dynamic system, but we can only learn from the existing data. And under this setup, so if we're provided with a data set of size n, that is n sample transitions from that dynamic system, then like this sample size n will induce a value gap of order 1 over square root n. And this order is shown, there is a statistical guarantee showing the upper bound of this order, and also a minimax lower bound showing that this cannot be improved in some very adversarial example. And those examples only involve the discrete state and action spaces. Okay. So, and like moving forward, if we are considering the online setting where we need to play with the system for T rounds, then the cumulative regret or the summation of this value gap will be of order square root T. And this is also shown to be minimax optimal by constructing some adversarial discrete state and action spaces, MDPs. And our a very natural question here is like these two orders capture the kind of the hardness for the discrete space MDPs, but when it comes to the continuous state action spaces, so does this like rates really reflects the hardness of the continuous problems. And so in order to assess these properties, we conduct a numerical experiment using the very classic mountain car example. Okay, so here is a car that is placed between two hills, and we want to use a force moving it leftwards or rightwards to help it achieve the flag on the hill. And that force can take value from -1 to 1, so this can be treated as a continuous action here. Okay, and here in this figure, we plot the value suboptimality gap versus the sample size of the offline dataset. And the red dot here is the average of some independent trails fitted by fitted Q iteration. And we found that in this log-log plot, so the value gap and the sample size form a relatively straight line when the sample size n exists some certain threshold. And we then use the linear regression to fit the slope of this line. And we found that so the value gap should be like proportional to the n to this number of powers. Okay, and this power is much faster than the 1 over square root n rate that has been predicted by the existing theory. So as we know, like there should be something like should be some more precise characterization of the phenomena here. And like that's the goal of this paper, to develop such a theoretical framework to help us understand this phosphate convergence. Okay. So, and this phosphate convergence is not like in this mountain car problem, it's not a very unique case here, because like, for example, in linear quadratic control, people have already shown that, so suppose the system identification error is of order 1 over square root n, then the value gap will be accelerated to the order 1 over n. Here n is also the number of observations from the linear transition system, and like this suggests the possibility of such an acceleration phenomenon. And also in the very classic dynamic programming literature, dated back in 1979, people have also observed that the policy iteration algorithms can be viewed as some certain type of Newton type algorithms. And such a Newton type algorithm suggests there should be some superlinear convergence in the algorithm. Okay, so does that mean there's a question raised?
Yeah, that's me. It just I wonder whether these two things are kind of very different from each other,
Mm,
and whether you're gonna talk about it, because the first seems to be like a perturbation result. It says that if I know the system up to some accuracy, then I
mm,
can square that accuracy, and that will be my value gap. So that's like a property of,
yeah.
like the map that goes from parameters to, I don't know, regret or something. Whereas the other one is more like an optimization result. It says that, well, I don't have to work really hard to get some optimal, answer to my question.
Mm,
Uh, so it's like the two are not that much related, like
yeah.
different things.
Yeah,
Yeah.
so the two are, yeah, another are in this on this page, it seems not that related, because one is
Okay.
regarding the statistical error, and one is regarding the, like, the, if we already know the exact formula of the dynamic
Right.
condition, then there is some, like,
Yeah.
optimization, like, property, and we will
Right.
see that. So, like, in our framework can actually, like, first it can cover this case, the LQR case, like the
Okay.
LQR, like, analysis, and, like, it actually borrows the idea from this part.
But okay.
Yeah.
Let's see how it goes. All right. Okay. Thanks.
Okay, so, like, this part, like this Newton type algorithm, like, is based by observing that there is some certain Lipschitz continuity, or the smoothness in the system transitions, and
Uh-huh.
you will see later that in our work, so that, like, smoothness will, like, have a very accurate, like, characterization there.
Okay.
Okay,
Right.
thank you. Okay, so here is our main finding. Okay, sorry. So here's here in the superlinear convergence, in our language here using the statistical, like, arrow characterization, it also corresponds to a rate faster than 1/√n. Okay. So, like, here is, I just want to show that, so the fast rate convergence is kind of like ubiquitous in the, like, in the continuous control. And our main finding here is that, so we identified there here this inequality to explain such a fast rate phenomenon. So we show that the value gap in those continuous control problem can be upper bounded by the square of the Bellman residual. And this square term, this exponent here, is what we consider novel. Okay, because, like, in the previous literature, it typically only have one portion of the Spellman residual, so the upper bound can only lead to 1/√n, for example. And thanks to this square term, so if in for the offline setting, a data set of size n can then induce a value gap of order 1/n, because we are taking square of that 1/√n estimation error. Okay, and in the online setting, so if we're tackling a problem with time horizon t, so previously the regret bound is of order square root t, because it actually takes integration of the 1/√n. But now, if we're taking the integration of this 1/n, then it will lead to a logarithmic regret here. Okay, that shows the theoretical advancement, like, suggested by our analysis. Okay, and the other main finding in our paper is that we show that the underlying mechanism that enable this acceleration, enable this square here, is these two groups of stability conditions. One is called Bellman operator stability, and one is called occupation measure stability. And we will later see the exact form of these two stabilities in the later slides. Okay, so So here is an outline of our talk today. So we will first show that stable problems have fast rates, and this fast rate is introduced by those stability conditions. And then we will show that the stability conditions, which are dynamic properties of the transition system, and it is hard to verify in practice, but we have also provide a principled approach to consider the curvature of the function class. And so we found that so as long as the function class exhibits some curvature structure, and then that curvature will ensure the stability conditions that are required by the fast rate phenomenon. Okay. So in order to set the stage, so let's just briefly recap the basic definitions of the MDP, and so as to unify the notations. So here the MDP is defined in this way. We are considering an episodic setting where h is the length of the episode. And our goal is to find an optimal policy pi such that the return, which we denote by j, is maximized. And we only consider value-based methods in this paper, and we did not specify any specific value-based method, and so a Bellman residual minimization or the Fideq iteration or any method that can provide some estimation of the Q function can be applied to our framework. Okay, so we take these notations. The online state action value function is written in this way. And the optimal state action value function is just take the maximum of this on policy function, and the optimal policy pi h star is induced by taking the greedy policy associated with the Q function. And this formula inspires us to use this value-based method. So the first step is always to find an approximation of that Q star function, and then use that estimated function to find a greedy policy as the output of the algorithm. Okay. So now let's delve into the first part, how the stability conditions ensures fast rates. Okay. So here we first introduce these two groups of stability conditions. One is called stability of Bellman operator, and one is called stability of occupation measures. First, the Bellman stability. So let us recap the definition of this dynamic programming that help us define the Q function in a backwards manner. So it starts from the Q capital H, so the last stage of in the episode, and at the last time step, the Q function is just simply the reward, and we apply the Bellman operator afterwards, and it will help us to get the definitions of the other Q functions iteratively until we reach the initial time step of Q1. Okay, so if we just take a subsequence of this whole trajectory, and we found that if we start from a larger index H prime, and then we can apply these Bellman updates until we reach a smaller index H in the definition of this Q star function. And this is done by applying this Bellman operators. So now let's perturb the initial point in this subsequence a little bit. So instead of using a Q star H prime here, we replace it by some noisy estimation f H prime, but similarly, but for the same for the comparison purpose, we still apply this optimal Bellman operators, And this perturbation here will reduce in a perturbation when a perturbed outcome f tilde h in the here. And this f tilde h should be different from this qh star because the initial point here is different. Okay. And the Bellman stability actually says that the output of this updates of this Bellman operators should be controlled by the magnitude of the perturbation we first apply. And by taking some proper norm here, so this should be of some form of Lipschitz continuity. And the kappa here provides the Lipschitz constant to control how the output of the Bellman operator changes as a function of the magnitude of the input. Okay. And this type of flexibility is very important for the validity of the estimation of the Q function, because it suggests that a perturbation or an error incurred in an earlier stage in the dynamic programming will not incur like uncontrollable error in later stages. So if like this stability condition is violated, then we can never guarantee that the output of the dynamic programming really tell us any information of the system. Okay, any question on this slide?
Yeah, maybe just to clarify, so like by perturbation, like how do you quantify this? Are you talking about like L infinity norm distance between the two functions? Or?
Okay, so in our paper, so this choice of norm is kind of flexible, and like we suggest one option is to choose the L2 norm under the optimal policy at the stage H. So that can provide a valid choice for this kind of condition.
Okay.
Okay. Thank you.
Okay.
And we also like regard this Bellman stability as a backward stability because this dynamic programming is applied backwards in a backward manner. Okay. And like moving forward, so we now consider the occupation measure stability. So here is the definition. Here is a recap of the definition of the operation measure. So we start from the initial distribution of this initial state S1, and then we execute the optimal policy pi1 star, and like following the intrinsic dynamic transition P1, it will jump to another state S2 on the second stage. And then like following from this, like now the occupation measure at the second step, we similarly apply this optimal pi star 2 policy, and then it will transit to a next state S3. So like iteratively, we can define the sequence of the occupation measure in this way. Okay. So now let's also look at just a subsequence here, where it starts from a psi h star, and after applying this optimal policy iteratively, it will evolve to a measure of psi h prime star. So now we consider a twin copy of the previous subsequence. So it still starts from the same initial distribution, but now we perturb the first step of a policy a little bit and replace this pi h star by pi h, by a perturbed version. But for the remaining steps, we still keep using this original pi star policy. And due to this perturbation in the first step, so the output C tilt here is still different. And this occupancy measure stability is to control the divergence of this output distribution using the difference of this policy in the first step. And this this kind of Lipschitz continuity is controlled by this constant of kappa pi star. And we also thought intuitively we like believe this kind of occupancy measure stability is very natural. Like for example, if we are considering control a robot, so in the experiment, so if we just apply a small force or like push it slightly, then like the robot should still be on track, and it will not deviate from the intended trajectory too much. So that like suggests some stability under the perturbation in the policy. Okay. 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 And
I have a question. On these two conditions, like too strong, because from my understanding, you're assuming the problem is easy to learn from these two conditions.
So I feel like there is indeed some like problem that like this conditions does not hold. For example, in the like previous literature of like discrete state action spaces, like this condition does not hold for all those adversarial like lower bound constructions. And like but for like continuous control problems, as we will see later, so I've like introduced inventory control problems showing that like this type of like condition is kind of very natural for all those like applications. And also for the LQR, like these two type of conditions can like have their correspondence precisely in the in that LQR background. And also like our framework here, so we've still like working on wrapping up another manuscript, but like our framework here can produce the sharpest order of all those like required like complexity for the LQR characterizations. Okay. Okay, does that answer your question?
Yeah.
Okay.
Thank you.
Okay. Okay, so let's move on. So here we have introduced two types of stability conditions, one regarding the Bellman stability and one regarding the occupancy measure stability. And one is kind of a backward stability of the dynamic system, and one can be regarded as some forward stability. And equipped with these two conditions, then we can prove this main theorem in our paper. So the main takeaway here is that, so here in the right-hand side, this QH star norm is like just some characterizations of the structure of the MDP, and also these two Lipschitz constants characterize some dynamic properties of the MDP. So they have nothing to do with data. And the only parts that are affected by the data is this epsilon H prime here. So these two are the Bellman residual. And so if we treat all these structural coefficients as constant, then we can write this into a very simple form. The value gap is upper bounded by the Bellman residual taking the square. And the square explains the fast rate phenomenon that we have seen before in the experiment. and also like in our main finding. Okay. So here, let me introduce an example of inventory control to show that those examples are kind of natural in some operations management applications. So here is in this inventory control problem, we are considering a store that only has storage capacity of 1 unit, and every day we will do the following stuff. So first, we will observe the current inventory level, which is denoted by XH. And then we will, based on our observation of the XH, to decide the order quantity AH. So AH is the action that may involve purchasing or selling. So like A can take either positive or negative value here. And there is no lead time. So every time we make we can order, so it will be fulfilled immediately. And then so after we adjust this XH using this action AH, then we like kind of like tune the inventory level to some desired point, and then we will have some customer demand. This demand is drawing from some uniform distribution over from between 0 and 1. So it can take any decimal value there. Okay. And we are considering a loss sale model here. So if any customer demand is not met, then we will just lose them, and there is no back orders allowed. And for this inventory system, we're considering this management problem. So we want to minimize the total cost of the management over 3 days. And here the cost consists of 3 parts. So first is the ordering part, and also the holding and loss sale. And we want to like tune the proper level of inventory so as the holding and loss sale is like kind of balanced, and like we will not like spend too much for the unsold products, and like we will also not get too much penalty from those loss sales that is the demand not met by our current inventory level. Okay, so we can form this inventory management problem using an MDP. So here the state has 2 components here. One is the inventory level on that day, and the other component is the lost sales from the day before. And action is just the order quantity, and the state transition is defined as follows. So at the H day, we observe the inventory level and make an order quantity, and then like this adjusted inventory level will be used to meet the demand of the customer. So if there is still some product remains, then it will then translate to the inventory on the next date. So otherwise, it will incur a loss sale like shown here. And the reward here is just the negative cost. Okay. And for this inventory management problem, so the optimal solution is very simple. And we can show that the optimal policy is just a base stock model where we adjust the inventory to some certain point depending on different days. So for the first 2 days, for day 1 and day 2, we should adjust the inventory to 0.75 units. And for the 3rd day, we should adjust the inventory to 0.5 units. Okay. And for that MDP problem, so we also calculate the exact form of the Q function, and we found that they all lie within this function class. So there is some constant term, some linear term like scale with the inventory, the loss sale, and the action, and also a quadratic term that takes a very specific form here, and the coefficient before this this quadratic term is positive. Okay, and this special form of the function clause ensures that any value-based method produced by this function clause will correspond to some base models. Okay, because like so. Okay. Okay.
Question: is this specific to having 3 stages?
It is not very specific to 3 stages. So if you have like
Okay.
100 days, like I believe like the first 99 days will still be 0.75, but the last day will be 0.5.
And how about the form of the optimal Q function?
The optimal Q function will also have the same form, but so like it can kind of like due to our assumption of the uniformly distributed customer demand. So by taking the integration of all those uniform distributions, it will only incur some quadratic term, and not too complicated terms will be invoked.
So it's like specific to the distribution, but not the number of stages.
Yeah, right.
Interesting.
Yeah. So so that's just a like illustrative example. So I just want to keep that as simple as possible.
Yeah. Nice.
Okay. Okay, so now like what does fast rate convergence in this small simple application means? So here if we have some estimated policy pi hat, so because we're using that type of function clause for approximation, so every output pi hat should be some base dot model. That is, they should take the form of some base dot level minus the current observation of the inventory level. Okay. Sorry, so I forgot an X here.
Also, you need to take a positive part, like your current inventory could be above the base level, and then you're not taking any action, say, I suppose.
Sorry?
If the current inventory is above the target level, then you're not taking any actions?
Yeah, so like in principle, so the order should only be positive, but like in order to further simplify the example, so I also allow the order number to be some negative. So
okay, so you're discarding stuff.
Yeah. Also
Wow.
allowed to selling stuff, but like it just used to simplify the calculation. But I believe the phenomenon should be the same.
Really wonder. That's a really interesting twist. It would be something like just dispose these products, and maybe the optimal policy will never use that, but yeah, maybe it helps with the calculation or something. Okay.
Yeah, so I've also done like some calculations to find that so even if we only allow the positive or non-negative ordering number, so all the calculations will remain the same, nearly the same, but like it will have some very like annoying details there, the technical details there.
Right. I mean, like, yeah, of course. Yeah. Okay. Thanks.
Okay. So now we have a very simple form of the like the estimated policy. So all the estimation error now lies within this B hat H, our choice of the base stock level in the estimated policy. So using this estimated like B hat H, so we can write the value suboptimality gap in this form. So it is it is the sum of the estimation arrow on 3 stages, and they're all taking the square of the estimation of the estimation arrow. Okay. And like intuitively, so if we're applying estimation for the using that function clause with a data set of size n, then the arrow within this BH hat should be of order 1 over square root n. And then after taking the square, it will lead to a fast rate convergence, because now like the rate will like exhibit an order of 1 over n here. Okay, so that's a very like simple illustration of like the fast rate convergence phenomena here. And our theory shows that it is actually a result of the stability conditions. So for the Bellman stability, so like this part is the verification is kind of tedious. You just apply some standard calculations and found that so there is certainly some Lipschitz constant controlling such an update precision. Okay. And what I found that is very interesting is regarding the interpretation of this occupation measure stability. Okay. So now, like for the occupation measure stability, we are just comparing the outcome of these two different policy sequences, and these two sequences only differs on the first state. So like here in the pi1 hat, we use a base stock level b1 hat, but here we use the optimal one. And we are considering the occupation measure difference by comparing the integration over any task function within that function clause. Okay, so for the day 1, so that comparison between the occupation measure is given this way. So let S1 start from the given initial distribution psi 1. And then like we execute either pi1 hat or pi1 star based on the current S1, based on the current state. And we can naturally show that so this quantity can be controlled by the arrow, by the difference in the base stock level. Okay.
Wait, does this assume that somehow this function f is continuous or Lipschitz in the second argument, the action argument?
Yeah. So here we are considering a task function like within the function clause.
And the function, okay, so.
And that also I actually like ignored some of the rescaled like numbers. For example, like the left hand side should be rescaled by the norm of the f. Yeah, so like if we just, for example, treat the f to be some like a unit function, like
so here f had linear and quadratic components.
Yeah.
So the quadratic component would suggest an unbounded growth over unbounded intervals, but I guess your intervals are bounded or something.
Yeah, because here the storage capacity is like bounded. The x
right.
plus a like.
And then somehow you normalize with the coefficients here.
Yeah. Yeah.
Okay.
Mm.
Okay. Okay. All right.
Okay, so here then let's move on to consider the second day. So the second day, so we're comparing the like occupation measures for this state 2. And for one sequence, the state 2 is obtained by applying the pi1 hat here. And for this part is obtained by using the pi1 star. Okay. And we now analyze how does this choice of like policy on the first day affect our like distribution of the second second day. So the state of the second day can be written in this form. So after we adjust the inventory to this targeted level, and then we like realize such a demand, then the state on the second day will have this form. Okay, so you can expect that. So the difference in the distribution of S2 can be controlled by the deviation in the B1 hat here.
Yeah, this now also relies on the specific form of pi2 star that it's smooth.
Yeah.
Okay. Okay, interesting.
Okay. And what's like more interesting is regarding the day 3 and even for like ongoing days. So now we have like adjust the inventory level using this pi2 star. So like after adjusting the level to pi to for the like targeted inventory level on the second day, then like it will like what number we have ordered on the first day will never affect the outcome on the third day. So the occupation measure on the third day is the same even if we're using different pi1 hat here.
That's very lucky.
Yeah. So
it's basically sort of says that the control takes a very strong form. Yeah. It's like you can forget about the history in one step.
Yeah.
In a way.
Yeah. Yeah.
Like you're decoupling from the past.
Yeah. Yeah, but for that like stability condition, we just require this term to be bounded by like this one, the estimation error in B1 hat.
Yeah.
Yeah.
I wonder, for example, if you take Mountain Cat, and that seems to be so not true, right?
Yeah.
Yeah, like a lot of the robotics control problems will not have anything like that, and but this inventory control is really like, because somehow your control is really strong over the state. Yeah, it's like you can basically reset the system to any state you want.
Yeah.
In inventory control.
Yeah.
Okay, very cool. Property, but yeah.
Yeah, but like I guess intuitively, so even though this is a very lucky like situation here, but intuitively, so lots of the control problem can have some certain property that in the like optimal policy will calibrate and realign the forward trajectory to some intended ones.
That's right. Yeah.
Yeah.
Like some relaxation of this is expected to happen even
Yeah.
in
Yeah. So
other yeah. Like you have feedback control after all,
yeah.
and the feedback is trying to undo bad perturbations and keep you on some trajectory or something.
Yeah. Yeah. So
Interesting.
that's kind of the intuition I got from the analysis. So like if the system kind of had those sense of stability, then it will lead to some fast rate convergence.
Okay.
Okay, so here is a recap of our main theory. So after we show the connection between this stability conditions to the fast rate phenomenon here. So now let's move on to explain.
Are you seriously thinking that anyone had any time to understand what's going on here? What's this bracket? Sorry, but like, yeah, like I wanted to understand a little bit about this. Like, what are these brackets? Like you choose either this or that? Like the bonds, like
it's the taking the product of.
you have to take the products. Like you have both of those. And you actually like that it's a product because it's like that's how the errors get smaller.
Yeah,
Because if those numbers are already small, then you take the product of them, it's even smaller.
yeah,
That's sort of the idea.
yeah,
Okay, so one type of Lipschitz constant in one way and the other is the other way. You sort of need both. And this division by the norm, like that scares me a little bit.
yeah. But like, so for example, if like this one is very close to zero, then it means that so the optimal policy is also not that stable because
Why would zero have a special role here? Like shifting everything by a constant, like why you cannot make this arbitrarily big or something?
okay, so the very ideal like case, so this norm should be replaced by some variance in this q star function.
Uh-huh.
Yeah, so
Yeah.
it's like kind of like transforming like a free. But I'm like want to
Okay.
say that so if like if taking any action does not really cause any variation in the function value, then it means that in the behavior of that optimal policy is not that stable.
Uh-huh. Okay. Okay. Yeah.
Yeah, and
That's
and,
cool.
and I introduced this one just to enforce this constant are free of horizon and dimension. So after introducing this term, so this too can be treated as constant.
And so what you call Bamon residual is also interesting. So these F hats are obtained how?
Mm.
Like there is the line that says Bamon residual. Uh, I see F hat H prime plus 1 and F hat H prime there. What are
Mm.
those? What is F hat H prime here?
Oh, so the f hat so like it's kind of an estimation of the whole trajectory of the q function.
Is that
So, so
okay?
you can just like replace it by like q hat. So maybe that's easier to understand.
So the theorem actually says that for any sequence of F hat H prime and
Mm,
any sequence of policies,
mm.
this inequality is going to hold.
Yeah.
Okay, and then in a certain application of the theorem, you would like fill in these F hats and P hats in some way, and
Mm.
then okay, yeah, it's like the standard ADP type of result that like if you have errors. But here, what I see is that oh, okay, so it actually makes sense because it's like you expect this temporal consistency that your f hats should be so that if you're applying the Bellman optimality operator on the f hat of the next stage, then you get the f hat of the current stage. Okay, got it.
Okay. Yeah,
And
so mhm.
yeah, like there were some assumptions about the norms of like for the value functions and the occupancy measures that they are duals of each other.
Yeah, so like specifically like this a norm is chosen so that the transition operator under the optimal policy is a expensive operator.
That was a requirement
Oh, that
for
was
the
the
theory.
requirement.
Okay,
Yeah.
okay, okay. Interesting. Yeah, thanks.
Okay, so maybe due to the time constraint, I will only
Ah,
go through this part like very quickly. So
okay.
just show you one slide here. So want to show the intuition behind that phosphorus phenomenon. So how does the stability condition like lead to the phosphorate? So our theory, our proof is developed based on the very like widely used telescope bound here.
Uh-huh.
So here's the value gap, the Bellman residual. And we found so there should be some certain cancellation between this occupancy measures using our stability conditions.
Okay.
So our work shows that so the norm of these two the difference of the expectations should also be of the same order as the Bellman residual.
Interesting.
Okay.
Yeah.
And this leads to the fast rate 1 over n because one portion of Bellman residual and the other one here, and the like taking them together will lead to 1 over n. And the standard use is to either use the pessimism or optimism principle to drop one of the expectation here. So after dropping one part of the expectation, then only like one part of the here only one part in the difference will like exist. Then like because there is only one Bellman residual remain in the span, so that will only lead to the slow rate.
Interesting. But usually, like you do this so that you gain with the coverage condition.
Yeah. So, for example, in the pessimism in the offline setting with pessimism principle, maybe I can show you like one or two slides later. Yeah.
Okay.
Like for the pessimism principle, we have this guarantees with high probability. So this corresponds to like the Bellman residual to be non-negative, so that this part is can be like nullified and upper bound by 0.
Okay.
So the only remaining term here is the like this expectation with respect to the pi star, and and that leads to the like the existing literature here. Yeah, and you can see like also very naturally. So the coverage will, in terms of the like this like occupation measure under the pi star and the data distribution.
Okay.
Divergence here. Okay. And but for the optimism principle.
But wait, like I said that like you're gonna have something to say about that, like do this, don't do this. Like, is this now just telling us that there's a trade-off, or like this is a slower rate? Like it seems worse, but at the same time we gain on the condition. So
yeah.
Is there a resolution to this?
So I kind of got some intuition from the LQR control. So they also have some slow rate like results, and also I also have some fast rate result like I've shown before in the literature review slide. And they shown that so it is believed that when the sample size is relatively small, then maybe the pessimism like to mitigate those like an exploration risk is kind of beneficial. But after the sample size n reach some certain threshold, then like those pessimism principle or robustness like designs will not be very like useful to like for efficient estimation.
Okay.
Yeah, so I believe like so the ordinary analysis to nullify this part like can apply to a smaller sample size, but our analysis, like with those stability conditions, it corresponds to a later stage where there is a pilot estimate of the policy that is relatively close to the optimal one.
I guess my question is pessimism really bad for you if you actually want to get a fast rate, or is it just a bad analysis of pessimism because of which we don't get the fast rates under, let's say, if you have stronger fortified coverage conditions?
So like from my understanding, so like because here the pessimism like kind of calibration is also of the same order of the Bellman residual. So even if we apply the pessimism principle here, like using that stability like conditions will also lead to the same guarantee, but maybe the constant will be but the constant might not be be optimal.
Yeah, but like we will get the fast rate for pessimism too,
Yeah,
right?
yeah,
But
right.
pessimism also, yeah, like under stronger coverage conditions and under weak coverage conditions, pessimism will have like the slow rate, and like the other procedure may not have the slow rate.
Yeah,
Okay,
or maybe
I
other
think I
like
understand
certain,
now.
yeah,
Okay,
maybe certain equivalents will just like kind of have exploding
yeah,
arrow because there is no like no a treatment of the like the like risk there.
okay,
Okay.
okay, got it.
Okay,
Yeah,
so
thanks.
I'm like kind of wondering, so how many minutes do I have? Do I?
Maybe you could wrap up in 5 minutes more. So,
Okay, sure. Maybe like
thank you.
so here is just I'll show you like maybe let's just finish this part. So if we're considering the online setting, then for the optimism principle, so this part is now negative. And so we should nullify the first part. And by some like self-regularized argument here, so we can show the regret, which is taking the summation of all this value gap, will can be bounded by square root t. And the square root t order is because we only contains one share of Bellman residual here. And for our analysis, so we tackle this difference by considering the cancellations. And this cancellation is enabled by the stability conditions. And in our framework, so there is no need to consider either pessimism or optimisms. So like certainty equivalence is regarded as efficient here. Okay, I think that's all for today's talk. Thanks so much for your questions and like thanks so much for joining us.
Okay, yeah, thanks.
Yeah.
Thank you.
All right. I do have a bunch of questions, but I don't know, in the interest of time,
Yeah.
maybe we speak at your reps.
Sure, definitely. I should like send you a mail to schedule a meeting then.
Yeah, that would be fun.
Yeah.
Okay.
Yeah.
All right.
Let's stop it here then.